Back in my day, there was something called the Commodore 64, a personal computer used for pretty much anything a modern computer is used for, but in a much more limited way, of course, but including gaming. But back in those days, mice weren't really the ubiquitous control scheme that they are now. Even the Macintosh was just starting to get its ball rolling. When I used my Commodore 64, I used a joystick, sort of like a flight controller. In fact, it was great for flying games, although I never played those. But nowadays, gamepads are everywhere. Computers use mice, or trackpads or whatever, and while some games use keyboard and mouse on the computer, consoles and people on PCs who like this use gamepads. And on these gamepads are thumbsticks, which are basically joysticks. Two axes, left and right, up and down, horizontal and vertical, that you can use for analog input. They're pretty good for driving. And I have here a thumbstick made for prototyping. Now, of course, this is not representative of what a thumbstick actually looks like inside your gamepad. This is what's called a breakout board, again, for prototyping. A breakout board is a miniature PCB circuit board, and it's called a breakout board because what would normally be soldered to traces just like this and would go around the circuit board with just the little copper lines are actually, of course, on here, they go on those little lines, those traces, but they go out to these 5 pins. So you can use it in something like a breadboard. So you have these little wires. Usually I'm using the header wires, the male-to-male ones, to connect between the breadboard, but there's also female-to-male ones. I actually got these by ripping apart a ribbon cable. That's a great way to get these. If you don't just buy a pack of them, find a ribbon cable, you can just peel them off of each other. But you take the female end and you stick them on these pins, and now you have a wire you can plug in. So you can use your joystick completely separate from a circuit, and there you go. So it's difficult to see, but you can move the stick in this direction and this direction. In this direction, it just straight up moves back and forth. And then there are 2 parallel lines. So the one direction it just moves, it just changes its angle, it pivots. So in this direction, it just pivots this way. And then in this direction, the mechanism that it's pivoting in actually pivots. And it pushes these 2 little copper or brass or whatever they are, perhaps brass, that pivots a different mechanism. And you can see here on the side, there are these little things that turn, one for one direction and one for the other. So you can kind of see that's your potentiometers. That's what this is. It's 2 potentiometers, just like a dial. And instead of being a knob you turn, it's this thing that you tilt. And then, of course, let me put this on because it's hard to press. Here's the little cap for it. Like a modern joystick, it also has a button when you press it down. And the way that works is there's a switch on here, and there's a little piece of plastic that sticks out from inside here. So you push down the middle, which pushes down the little piece of plastic that sticks out, and it's like a little finger pressing the button. It's kind of cool. So let's actually get this hooked up and see how it works. So I'm just going to hook up some wires to the pins on here. The pins are labeled ground, that's your negative terminal for your DC, plus 5 volts, so that tells you how much you need. And then you've got VRX and VRY. Those are referring to the horizontal and vertical axes. And then SW for switch. So I'll connect a red wire to the plus 5 volts. I'll connect a brown wire to the ground. I don't have a black one handy. We'll put a yellow one on the switch. Put an orange one on the X axis. And of course, which one's X and Y just depends on how you put it in your device. And then we'll put a green one on the Y axis. So this is the joy and wonder of a breakout board. We have a little circuit board with wires coming off the pins. And it's really handy to plug in. So let's plug them in. So I have here my power supply that we have set at 5 volts, 0 amps for safety. And now, there's one thing you want to check. First of all, remember short circuits. Now this device may or may not have any sort of internal resistance across the power. Of course, it's going to have resistance across the X and Y axis outputs because those are potentiometers. But remember, if you turn your potentiometer all the way to 0, so you push the stick all the way one side, then you have almost no resistance, which means you have a near short circuit and a lot of current flowing through. And everything has its power limits. You don't want your stick to melt in your hand. So there are many ways to test this. You could put this across your resistance meter, but that only works for ohmic devices. This is an ohmic device because you've got a switch which just connects or disconnects, and 2 potentiometers which are resistors. But if you have a more complex device, device, you might have diodes and everything else in there. So that's when you use your power supply with a current limitation, because 1 milliamp, even if it's going through a short circuit, is not going to hurt anything. So the first thing we're going to do, we're going to pretend that this is a non-ohmic device. So I'm going to straight up hook the power on. This is not using any of the sensors. This is just the positive to the negative. So we'll turn it up to 1 milliamp, and we'll watch. It looks good so far. So you can see it's going up very slowly, but that's actually, it's still going up. That's just the way this thing is designed. If you give it a higher limit, it'll reach faster, but watch when it goes down. It's still less than a milliamp. So, you know, of course, you might want to be safe, but if you see it going up slowly like that, but it's still going up, give it another milliamp or so. You know, I'm sure a better quality power supply would have less of a problem with that. But the point is, it's still less than a milliamp. So that means there's definitely internal resistance. And since this is an ohmic device, we're going to go ahead and measure it. So take it out of the circuit with your power. Never measure resistance when there's any power, including just the regular diodes in here. So I'm going to put the red positive into that trace and the negative into this one. And then we'll connect my multimeter. So we take the red, connect it to the positive here. We'll take the black and connect it to the negative. And I've got it set on 200 kilo ohm setting. We're getting 4.5, so we can definitely turn that down. 2, see, that's too little. So now I'm on the 20 kilo ohm setting, and it's reading about 4.55 kilo ohms. So that is essentially a resistor that's just in this thing. And everything that goes through it has that resistor, which means we don't need any external resistors whatsoever for reading the axes. Now, you still have to test the switch separately, which we'll do because you never know what bypasses anything. But we know that the power straight up does not need any resistor. So that means I can go ahead and take this and hook it directly into the power feed with nothing else. So the red goes into the positive and the brown goes into the negative. So we'll go ahead and turn this back up, set my limit at 10 milliamps, and it will go down to 0. And I wiggle it around. You can see it's not drawing anymore. All right. So let's go ahead and connect our other pins. So the orange was the horizontal axis, which I'll just put there. The green was the vertical axis, the y-axis, which I'll put there. And the yellow is the switch. We'll worry about the switch in a moment. So the axes are radio potentiometers, just like my potentiometer video. If you want more details about potentiometers, go watch that video. But basically, we're going to measure voltage. So let's set this on 20 volts, because the next lowest setting is 2 volts. And we got 5. And we know we don't need any sort of resistor to make sure that there's no short circuit when the potentiometer is at 0, because there's already resistance on the power supply. So this is going to divide the voltage. So we'll take our red meter and I'll hook it up to the x-axis and the black end of the meter to negative. And we'll see when I'm not touching the stick at all, we get 2.5 volts. If I touch the stick that way, we get 0. And if I do it this way, we get the full 5. And you can see it's going up to 1 milliamp and going back down, but I have it set on a limit of 10, right? So we know, we've confirmed again that the internal resistance is working. Going back and forth wiggles it no more than 1, or if we're rounding, 2 milliamps out of 10. So this is how you measure the x-axis. You might put this into the input pin of an Arduino, or whatever your circuitry is if you're actually soldering this down. And if the voltage is 0, then it's all the way to the left. If the voltage is 5, it's all the way to the right. If it's in the middle, then it's 2.5. And there you go. You can see it's a linear scale. And you can check that just because you've got left, middle, and right. Left is 0%, right is 100%, and middle is 50%. If this were logarithmic, then that middle point would not be at 50%. 0% would be 0%, 100% would be 100%. That's always true. But on a linear, in the middle will be 50%. Anything else, it will not be. So we know this is linear. So let's do the y-axis. I'm just going to move the red probe over to the y, leave the black, and we're seeing a slightly different voltage because the resistance is not exactly the same. Everything's approximate. So I'll put the left and right. See, it's not measuring it. Do it up and down. Up is 0, down 4.99. So that is how you measure your y-axis. And of course, if I felt like setting up my other multimeter, I could measure both at the same time. But what about the switch? First of all, let's make sure that the switch has some resistance. So we're going to do just like before. I'm going to turn my current down to 0. Then I'm going to connect the switch directly to the negative power, and I'm going to turn the current up to 1 milliamp. And of course, it's going to draw from the rest of this. In fact, the switch is open right now, so nothing's going to happen. So let me just turn this up so it gets up to 5. Oh, it needs 2. And it's not even drying 2, it's just the way this is working. So once again, this is not a great power supply, but it gets the job done. So now, let's close the switch and see what happens. Click it down, click it up. Looks good, it's not really jumping. So let's turn it up to 10, and we'll do it again. And it's perfectly fine. So that means that it's still going through the internal resistor. So every single output here is connected to some sort of resistance to make sure that it doesn't draw too much current, that there's no effective short circuit, which means this is nicely designed. So let's actually test the switch. So I'm going to hook up the switch to the positive of an LED, the negative of the LED to the negative power. Nothing happens. But then, click the switch. Nothing happens again. So now we do sanity checks and make sure our wires are good. So what I've done here is I have connected one end of my meter to the power pin and the other end of the meter to the switch pin. And right now we're reading a horrendous amount of resistance, which means an open circuit. But if I click the switch on the 20 kilo ohm setting, we get 4.57 kilo ohms, which is roughly the resistor that was in the thing anyway. Let's confirm that. If I switch the measurement to going across the power and ground, we get 4.57. So it's clearly connected inside. The button is working. Now this is interesting. I removed the grounding pin, the 0 volts, the negative, so that's disconnected. And if I press the button now, the LED lights. But if I put that back in, the LED does not light. And now I have discovered my mistake. I have forgotten something called a pull-up resistor. We'll get to that in a future video. But what I have done is I have connected a 10,000 ohm resistor. I have gone from the positive power to one end of the resistor, the other end of the resistor to the input, if we're viewing this as the input pin of an integrated circuit. And now you'll see, of course, our limit is set at 10, so it's still drawing only 1 milliamp or so. And of course, I have the meter set up to the x-axis, so that's still working. But basically what happens is this reverses the switch. When the switch is open, there's a circuit and the LED lights. When I close the switch, it connects to ground instead through the resistor, so it's not drawing too much power. You can see it is, though. Watch the limit go up. When I press the switch, it goes up to 2 to 3. The limit's at 10, so it's still resisting. The power supply is not limiting the current, so it's not drawing more than it's supposed to. But in this case, it's going through the LED. In this case, it's just connected from power through a resistor into ground. So that's how you use the switch, with a pull-up or pull-down resistor, and then your axes follow normally. And that is your joystick. You've got 2 potentiometers and a switch. And you can plug that into 2 analog and 1 digital pin on an Arduino to read your joystick. Of course, you make an actual joystick and solder it together. You can connect it that way. But there we go. And you can see we're reading a negative voltage because of these diodes. Turn it off. There you go. Like I said, sometimes you discover fun things in the process of making your videos. I had tested this prior, but I had tested all the pieces in isolation. I had not hooked the entire thing up together and tried them all at once. This really is a documentary of my learning process, and I hope it's useful to you as well, because I cut out all the fumbling and just tell you what I did. So we've discussed potentiometers already. There's a video on that if you'd like to look back there. It's the same thing here. There's just 2 potentiometers, 1 for each axis. The one last thing about the joystick is if you've ever used a gamepad, the thumbstick, if you've ever used a gamepad with thumbsticks, you'll notice you put them in a circle. And this one too. It's got the little metal nubbin in the middle that is restricted to a circle. Now, both potentiometers go to full axes, and you could have it a square if you want, and you'll get your full range. But there's 2 reasons to do it this way. First of all, if you use your geometry and think about Pythagorean theorem, then you've basically got a circle of constant maximum radius. So no matter which way you push the stick, if you take the 2 axes together, you get a point on a circle of constant radius. So if you measure the distance between the center and whatever your x and y axes are reading as if it was a point on a plot of x and y axes, then you will always get a certain maximum distance. So you could map this into how fast your character runs or your ship flies or whatever. But the other reason is, let's say you're pushing the stick one way and you want to change, you want to turn a little bit, sort of like if you're driving game and you want to change your steering. Pushing it around a circle is pretty easy, but around a square it would be rough. Even if it normalizes so that the speed is always equal no matter the angle, it's hard to get it at like just short of a diagonal because it'll be pushing up against. And it's hard to get it around the diagonal because you're stuck in a corner. So that's why a circle. You sacrifice the maximum measurement capability for better usability. As for pull-up resistors, we'll discuss that later, as well as something called debouncing a button, because a button is not a perfect thing. You don't notice it on a human time scale, but if you measure the actual closing of a button, when you press the button it goes like and then it settles. So if you're just having a computer measure every time a button opens or closes, you might get multiple presses. We'll worry about that later. For something like this, it doesn't matter. But until those videos come out, be seeing you.